but that all depends on where you are in the world. And welcome to today's Aviation Week webinar. This is how JetZero is driving innovation for the DoD's digital engineering and MOSA mandate. It's sponsored by Applied Dynamics. I am Ed Hazelwood, and I will be moderating today's event. We have just a few announcements before we begin. So this webinar is designed to be interactive. So interactive means as a participant, we really kind of expect you to ask some questions. You'll have a way to type that. There's a DACA widget at the bottom of your screen. It will allow you to learn about today's speakers, to download resources, and to participate in the Q&A session that'll take place at the end of the presentation. So the slides are going to advance automatically throughout the event. You can also download a copy of the slides via the resources widget. And towards the end of our webinar, we will ask you to complete our survey. It's found on the right-hand side as your feedback provides us with valuable information on how we can improve future events for you. And lastly, if you are experiencing any technical problems, please click on the help widget. It's found at the bottom of your screen. And or if you prefer, you can type your issue into the Q&A area, and we will be glad to offer you one-on-one assistance, okay? So now on to the presentation, how JetZero is driving innovation for DoD's digital engineering and MOSA mandate. Discussing today's topics are Bethany Davis. She is the head of airplane systems at JetZero. Scott C. James. He is the president and CEO of Applied Dynamics International, ADI. And Stephen Landers. He's the head of labs at JetZero. So if you'd like to learn more about our prestigious panel of speakers, be sure to check out their impressive bios in the speaker bio widget found within the webinar platform. And so with that, let's go ahead and get started. So over to you guys, Bethany, Scott, Stephen, let her rip.
All right. Like you said, good morning, good day. It is my privilege to share with you the JetZero mission, share why we are doing this and why this matters. My colleagues and I are asked why we would leave established OEMs, major players in aerospace and defense, to join a startup. And the answer is that we are not just any startup. We are not trying to address the corner of an existing market. We aren't trying to create a new market. This market is massive. And we believe that the world truly needs this airplane. We see so many tangible benefits for the operators, for the supply base, for passengers, US manufacturing, and for the general public. So back to why are we doing this? Because we see a huge problem that's really best illustrated when we look at history. You know, prior to the 707 or the 367-80, to be specific, we had so many different airplane shapes. We had tailwheel airplanes, we had biplanes, we had internal combustion engines with propellers, we had fabric and square fuselages. Just the shape of airplanes changed so much in the first 60 years of powered flight. But really for the last 60 years, the shape of an airplane has remained the same. So swept wings, potted jet engines, and pressurized cylinders. That isn't to say that there has been no innovation in aerospace in the last 60 years. You know, our avionics are dramatically safer. So we've added TCAS, TAWS, RVSM, ROAS, GPS, LPV approaches, and so much more that is added to the safety and efficiency of our aerospace network. There's also been innovation in structures, you know, back from the stitch fabric of dope and fabric to riveting metal, to riveting composites. And of course, our engines are much more efficient. But now the gains that we've had in the last 20 years have really come at the cost of durability and maintainability and profitability of our airlines. So we have to look at other places to innovate. And that's why we say the airplane shape is the innovation. It gives us, with existing technology, so existing engines, avionics, other airplane systems, a 50% reduction in fuel burn. And 50% is a huge number. So especially when put in context of previous new airplane introductions, and the fact that, I've worked at an airline and the whole internal team was focused on how can we do things to optimize our fuel burn. So saving low single digits is really a big impact. So 50% is huge. So how do you talk about 50%? There's really so many different ways that we could show this. You can show per passenger, per mile, per trip. One simple way is really comparing monthly fuel costs. So using the 787 as an example with our Z4 airplane, we can save the airlines more than $1 million per month per plane. But really, our plane will only have an impact if it's actually in service. So a major program requirement we have had is it has to fit into the existing infrastructure. And by infrastructure, I mean both physical, so airports and airspace. So using the same existing runways, taxiways, gates, jet bridges. And when we talk about airspace, we mean existing altitudes, existing airspeeds, same navigation and communication procedures. But it also means the existing regulatory infrastructure. So our airplane will show compliance to FAA Part 25 transport category airplanes, be operated by the airlines under Part 121, and be flown by airline transport pilots certified under Part 61 for airplane multi-engine category and class. So this is existing regulations. The goal is no new regulations, no SFARs for this airplane to really fit in between the airline's existing fleet of single and twin aisle airplanes. And that's exactly where we've positioned our plane, is in the middle market. We see that the demand of the largest single aisle dominates the market for orders and deliveries. And we believe that providing airlines a middle market airplane really meets their needs. And there's currently no supply from the entrenched incumbents. We also know that the passenger airline market is not the only mission that could benefit from our airplane. We see both cargo and military missions both having real tangible benefits. And that's why in conversations with our Air Force customer, our plane fits in not only as a tanker, but really fulfilling a large number of air mobility missions. So from airlift to medevac, et cetera, it really all comes down to the capabilities of our airplane. To say it simply, our plane provides twice the payload at the same range, or twice the range at the same payload as the Air Force's existing fleet. And that is why the Air Force has awarded us a $235 million contract to help us in our efforts to build and fly a full-scale blended wing airplane. The goal of this airplane is to prove to the world and to ourselves that this shape does everything that models, the CFD, the wind tunnel data, everything it says it will do. Just like the 367-80 proved that the tube and wing was the next commercial airplane, we believe that our full-scale demonstrator will pave the way for blended wing airplanes to be the future of commercial airplane shapes. And that's really because right now is the time for a full-scale prototype. The industry, in partnership with NASA for more than 30 years, has flown multiple scale models with what we lovingly call the godfathers of the blended wing design. So we are so fortunate to have Dr. Bob Liebeck, Mark Page, Blaine Rodden, and others, Dr. Alon Crow. They are on our team at JetZero now, and they were the original ideas behind the blended wing. And they've really been holding and passing the torch to us with JetZero. And because of them, the team has really grown. We have lots of disciples, not just the godfathers, lots of disciples now of the blended wing. And we have come from all over industry. So OEMs of airplanes and engines, we have operators, we have suppliers, we have, and now regulators. So some of our recent announcements of new folks to the team are Mr. Rob Dewar. So he was the godfather of the C-Series A220, and Mr. Steve Dixon, so now retired FAA administrator, former Delta. And we've also recently added Lirio Liu, who is now retired, former executive director of FAA aircraft certification. So our team keeps growing, and we keep getting just incredible people who believe that this airplane needs to come into fruition, come into service. And of course, we couldn't do that without our amazing supplier partner relationships. So they see the vision as well. We are highlighting today our partnership with ADI and all the digital engineering with the labs, but we have an incredible partnership. We've built strong contractual relationships with our suppliers, and many of them have already delivered real hardware that will begin testing in our labs that we'll hear about shortly. But it's so exciting that more than 3 years ago, giving a lot of these folks a phone call and really getting started on this journey that where we are now. But they're part of the partnership now because they really see the vision of what we're trying to do and the disciplined approach that we've been flying scale models since 2022 as JetZero. And as you saw, it's been since the 90s that there have been blended wing scale models flying. And we continue to build off of the scale model to do the full scale demonstrator that would be followed by the Part 25 certification of a passenger jetliner, then a freighter military tanker, and then for our namesake, with and when hydrogen engines, hydrogen fuel storage, then having a zero carbon emissions jet. And really, of course, we're all doing this, our internal team, our supplier partners, for our customers, the airlines, as well as the flying public. We believe in the power of travel and building relationships and knocking down barriers. And we believe that this plane will really help push aviation and aerospace into the future. Last year, the airlines, specifically Alaska, announced a partnership with us. And we have many more exciting announcements to come in the future as we all see and want to see that the shape of this airplane, of commercial airplanes, to change too. Thank you.
Awesome. Thank you, Bethany. Okay, well, as you can see, JetZero has an exciting mission that is a game changer for critical civil and military applications. Now, before we dive into JetZero's digital engineering strategy, we wanted to speak briefly about some movements that have been coming out of the Department of Defense that are very relevant to how JetZero is investing in digital engineering and very relevant to what we're going to discuss today. Now, in 2024, there were two events that caused our aerospace and defense community to look up and take notice. The first was the Army's unexpected cancellation of the Future Attack Reconnaissance Aircraft, the FARA, where reportedly one factor that contributed to its cancellation was an inability to show a path to MOSA compliance at the demonstrator phase of their project. This sent a message to industry telling us that MOSA was for real and not some buzzword fad that would soon pass. The second event was the Army's release of their May 2024 memo detailing what they call the Army Digital Engineering Directive. For us, MOSA is a rigorous systems engineering approach that starts by defining the system architecture and its data schema. And that opens the door for the implementation of a highly advanced, highly automated digital test enterprise, like we're going to talk about here today. We've been very encouraged to see that the DoD is so serious about digital engineering and digital engineering enabling methods and tools, including MOSA. So we are very excited to tell you about the leadership JetZero is providing to enshrine digital engineering best practices and a path to MOSA into their exciting Air Force-supported BWB demonstrator project. So now that is on to you, Mr. Landers.
Thank you, Scott. So yes, I'm Steve Landers, and I'm the head of labs for JetZero. And so what we're doing within our facility is we're building several different test labs to help accelerate the development of our airplane program. We have the Flying Qualities Lab, which is a simulation-only based, fixed-based operator type simulation. We have the Integration Test Facility, which is the avionics and electrical system test facility. And then the Ironbird, which is the mechanical and hydraulic and landing gear systems testing with full-up aircraft level hydraulics in the lab environment. And so through all of these, they all use a similar common backbone for the simulation architecture. And we're using these facilities to test and evaluate all the airplane systems before we get to the airplane. And the benefit of doing that, of course, is that we try and eliminate all the mistakes, all the problems, identify all the troubles that we're going to have with data communications between the boxes and the wiring in those in between all those boxes before we actually get to the airplane, so we don't have to solve it on the airplane itself. That way, we don't also have to wait for the airplane to do the testing activities. So you can see here on the bottom part the pictures of the Flying Qualities Lab. That's a picture from just a couple of days ago, where we actually have real structure in there, real similar secondary structures. We have the middle picture is the Integration Test Lab. Again, you see a very similar architecture to what's in the FQL. And we have all the avionics that we're installing into it. And then the Ironbird facility, we're in the process of building and designing all the structure for it. So we don't have a picture of it just yet. Okay. So the concept of the labs, of course, the biggest one is that we're trying to support aircraft first flight activity by the end of 2027. And so the big buzzword for that one, or the phrase that we're using for it, is solving for time. We want to do as much of this testing activity away from the airplane before we get to the airplane as much as we can do. And so what we are doing is taking the airplane wiring schematics and basically the point-to-point wiring diagrams for all the airplane systems. And we're digitally modeling those in the FQL, which is a simulation-only facility. And then we're taking the same wiring diagrams, the same schematics, and we're actually installing those real wires to equivalent lengths into the Integration Test Facility and also into the Ironbird, so that we can do a whole series of testing in both of those facilities. And the same exact wiring diagrams are going to be applied to the airplane demonstrator, of course. If there's any changes that are discovered, or any errors, problems, or things that we want to change, correct, or fix in any of the facilities, including the airplane, the wiring diagrams get updated, and then all of the facilities get those updates, and we continue testing so that everybody is in essentially the same configuration. This can greatly reduce a lot of risk for trying to do these things all at once on the airplane. And so the lab facilities, we can do a lot of testing before the airplane's actually fabricated and before it's built. So lab facilities right now are in process, like you saw in the photographs. The demonstrator hasn't quite gotten to a state where we can do any real testing in that area. So the labs give us that time opportunity to do testing before the airplane's available. So within the ITF itself, this is a basic 3D architecture of how the lab is configured. The facility there's a wall that's actually between the flight deck section and where all the signal conditioning cabinets are, which you see on the right side there. And all the wires that come out of those cabinets and go through the cable tray system, go into the cockpit, so that we have real production equivalent displays, controls, buttons, switches, We have actual flight control sticks, the active control sticks, throttle quadrants. We have as much of the real hardware as possible inside of this test environment. And then we drive an out the window visual system so that it gives us a good pilot perspective as to what the flight crews will see outside of the airplane when they're actually doing their flying in the labs. Again, one of the other things that we can do within this environment is that we can inject all kinds of failures that you wouldn't want to put on the airplane. So, we can fly at 50,000 feet or put the airplane at 50,000 feet in the simulation, and we can shut down both engines and see what happens, see how long it takes to fly down to the ground, predicated on what our simulation assumptions are and all that. Stuff that you wouldn't want to do to put the actual airplane and the flight crew at risk. We can do those tests in the lab all day long, numerous times, and develop emergency procedures or other mitigation for any of those conditions. So inside of this environment, we have a ground power unit that provides equivalent aircraft electrical power. So we don't have necessarily all the dangerous, hazardous materials like engines running or APU running. We have substitutes for that so that we can make it look just like what it would see on the airplane. Okay, let's see here. So with our test process, our systems teams are generating requirements, which are stored. Our tool that we're using is Siemens Team Center. And so we've got a repository of all the requirements. And from those requirements, we're looking at building test configurations and initial conditions that we can automatically run within the lab to do a quick start basically for the simulation. Additionally, we'll have test procedures, automated test scripts to run a series of tests that we want, like instead of having to have a human interface manually executed test procedures, we can run a script and run the same test procedure over and over again that can evaluate any changes much more quickly than having to do something by hand with an interactive test procedure. So then all the results from those, they go into the test execution. So we run those with the automated scripts. We get data analysis and collection that is mostly an automated process. And then all that can be taken with the requirements out of Team Center into report generation. And now we can go from having our test procedures and all that to report generation in a relatively quick period of time for those kind of tests that don't require time critical activities like flying an approach. You don't want to do that necessarily in a full digital accelerated mode or to do some of the things that require human interaction. But we can do the other tests for other systems that don't require time critical events through an automated process. Let's see here. What else can I say? So again, we have Team Center for our requirements. We're also using Team Center for the V&V modules and potentially even for some of the additional process management. And so we're doing mostly manual from requirements into test procedures and configuration, but most of the execution is all automated. And that's going to help us to solve for time. So that's kind of the overview of this slide, which is the digital test enterprise, which Scott can talk a little bit more about here also.
Thanks, Steve. Yeah, test automation really is the name of the game. Steve speaks about solving for time, and what we're really trying to achieve is tremendous cost savings during development, and then later on through sustainment of the airplane that translate into lower operating costs for the commercial and the military operator. A high performance digital test enterprise needs to allow for fully automated test execution, fully automated data gathering, results analysis, and report generation. But the digital test enterprise must also support critical pilot and loop testing. However, pilot and loop testing can also benefit greatly from heavy automation. Automation of things like test initialization, doing cross-system readiness checks, other automated testing features, all in support of that pilot in the loop. In this slide, we look at the use of a test sandbox approach, where simulation models, test parameters, test automation language source files, and the likes are checked out from a tightly controlled file repository, and then a distributed multi-server test framework is compiled. It's built into a deployable package of Linux executables, configuration, and connection files, and more. Test frameworks are then initialized, deploying the real-time apps across those distributed Linux servers that are in the labs that Steve showed us quite nicely. And then next tests are executed in a fully automated or semi-automated pilot and or crew in the loop mode of test execution. And then finally, data is collected, results are compiled into automatically generated test reports that show green light, red light, pass-fail status. And all data and documents are pushed to their enterprise file storage destinations. And then the sandbox may be deleted and rinse and repeat as needed. Our next slide here illustrates the map of our aircraft integration, I should say airplane integration automation language. At the top, we see airplane level test cases and test maneuver functions. The airplane level test automation language is used to perform the kinds of testing we think of when we think of flight test. This includes things like takeoff and landing tests, controllability and maneuvering tests, and other tests that stimulate and evaluate multiple airplane systems at once. The big blue block in the middle speaks to the system level test language. So the system level test language is divided into test cases, test maneuvers, and low-level test interface functions specific to a given aircraft system. So you can see that includes the flight control system, engines, avionics, and on, as you can see across there. Test requirements for each system are driven by that system's engineering group and linked to the system's requirements, like Steve mentioned, using Team Center, etc. Finally, the test language is rounded out with functions for managing the test frameworks, automatic health check of the edge computing frameworks, enterprise system interfacing, like the file repositories and data repositories, and then test analysis and reporting. So, and for the information of the audience, we now have standardized on using the Python coding language for test language implementations for more than a decade, and there's lots of good reasons that we've gone that way. So now we'll take a look at a new capability that we are working to develop in support of the JetZero test labs that we call the Test Pilot Digital Twin. The Test Pilot Digital Twin is an advanced capability allowing for a level of automated testing and a level of rigorous safety evaluation that is well beyond the current state of the art for civil and military aircraft today. And is a great example of digital engineering technology that can be leveraged broadly to achieve tremendous return on investment. So on the right-hand side of the drawing, you can see the green boxes, which represent the aircraft systems that we are integrating and testing in JetZero's ITF lab and in other labs to a different extent. And during normal simulated flight test operations, the pilot interfaces with those integrated systems. You can see our pilot there in the bottom left. You've got to have a stick figure on a good systems engineering drawing. But the pilot interfaces through those integrated systems, through the flight deck controls and indications, including, as Steve mentioned, side sticks, throttles, pedals, and so forth. The Test Pilot Digital Twin enables automated testing by electrically switching the signals or switching the signal lines between the aircraft systems and the pilot controls, replacing the pilot controls with simulated pilot, a simulated pilot driven electrical emulation of those signals. This allows us to perform extensive automated testing overnight, on weekends, and remotely. But there are a lot of really exciting and unique features around the approach being taken. One of the unique elements of this technology is the approach for pilot modeling. And Steve, I think it'd be helpful for you to speak to the way we're structuring the pilot model. Why don't I hand that to you?
Okay, yeah. So what we're going to do is we're establishing some of these test scripts to do some of the very basic pilot functions. Like we're going to start off with the very, very simple things where our digital test pilot twin can fly straight and level and maintain airspeed, and then we can inject on top of that any of the failures and see what the behaviors are and characterize all those. And then we'll create more scripts to provide the digital pilot the ability to fly other maneuvers like constant altitude turns, or at some point we expect to be able to do fully automated digital pilot approach to landing, similar to the technology that exists right now for automated landing under Cat 3 approaches for instrument approach procedures right now. But we can do other things where we can automate the input of doublets for any of the control axes. We can do things like throttle changes, or sequencing of systems throughout the airplane, things that a normal pilot would do either with a switch or a button push or some other control input. And instead of the actual physical push of the button or whatever, we'll have the script that actually injects the electrical signal into the avionics system and causes that performance, that behavior to happen.
Yeah, awesome. And then, and it's worth mentioning that both Stephen and Bethany are, in addition to their day jobs, are pilots. So they know a little bit about what they're talking about across the board. More than a little bit, I apologize. Now, Bethany, I know you've got some really strong experience around how pilot modeling can be leveraged to improve the design of the performance of the aircraft, et cetera.
Yeah, I think what's really exciting, in addition to, it's been an industry where modeling systems and doing the integration, but then creating that model of the pilot. So right now we design a lot of the systems, flight controls and control laws, and then the pilot tests it, which we will continue to do. But I think there's a really great step in between of modeling across a wide spectrum. So the idea is that, not just experimental test pilots can fly the plane, but a line pilot, a regular day-to-day line pilot is very comfortable flying this airplane. So getting to have numerous human test pilot data points as a simulated digital twin is going to be a great help to us as we continue to refine how the system is designed, and not just come to the end and we have a handful of human pilots doing those tests.
Awesome. Well, and by the way, to the audience, we are actively looking for defense innovation funding to design and build this test pilot digital twin that will be leveraged in JetZero's Flying Qualities Lab, the ITF, and the Ironbird, as well in a form in the virtual test platform. Okay, and before we move on to I guess I'll hold it at this slide. Before we moved on, we to a quick discussion of lessons learned. We wanted to touch briefly on MOSA, the modular open systems approach. I don't plan to give a primer on MOSA, so if you're not familiar, I apologize. This next minute is not for you. So please bear with us. As I said earlier, we see MOSA as a rigorous systems engineering approach that starts by defining the system architecture and its data schema. And then that opens the door for the implementation of a highly advanced, highly automated digital test enterprise, like we've been discussing. A well-defined system architecture and data schema allow us to design virtual test platforms, rig-based test platforms, like what we talked about today, that provide a modular COTS hardware and COTS software platform that will allow for MOSA compliancy to be driven. It'll allow testing for compliancy, and ultimately allow for one vendor's aircraft systems to be swapped out for another system with minimized integration and sustainment costs through that extended life cycle. We look forward to sharing in the near future our progress with MOSA design on the JetZero Z airplane platform, and linking there, and how we are linking their digital test enterprise to that MOSA architecture. So if you're interested in continuing the MOSA discussions, please feel free to reach out to me at ADI. You can go to the ADI.com website and reach out. So next, we wanted to have, before we move into Q&A, we thought it would be good to have a little panel discussion between us around lessons learned, in the digital engineering space. Bethany, you want to take the lead?
Absolutely. One of the lessons learned that we've had is that our suppliers can do a great job of providing us a new software load. So whether that's a blue label load or a red label load, and we need to do the testing. In the past, it takes test engineers, and a software load can take 6 weeks of testing with humans injecting various failures and then writing down what the results are. That's been a huge thing where we want to turn from 6 weeks of testing in the lab to then weeks of report writing. We want to, the plan is we are automating those test procedures so that we can turn 6 weeks into overnight or even a couple days, and that it's automated report generation. So that was another thing in the past of, you can complete the testing and then get told it's 6 weeks to write all the test results and test report. So trying to do as much automation as we can to really set it up and have the tools so we can turn around software loads much quicker.
Excellent. Steve, you're up next. How about you?
Some of the great experiences that we've had have been where, again, solving for time, where with putting all this stuff into a lab environment with some other program goals to try and deploy a test asset or test article into an environment, into something like an air show or whatever. If the test article itself, if the actual airplane isn't available yet because it's still being built and still being flight tested, doing some of the other systems testing, like for example, cabin management, you couldn't put cabin management into an airplane until the airplane was, down and resting from the flight test. You'd have a period of downtime for it. So you couldn't troubleshoot anything until you had the airplane on the ground, which impedes the flight test program. But if you have a lab like this where you can integrate and do all that data communications and verify all the system performance, then you can do that in the lab, and then it's just basically kind of a cut and paste to put it into the actual airplane. And from previous experience with another company, we were able to do that and accelerate the development so that they were able to meet specific goals for schedule that were absolutely unheard of industry-wide at that time. So it greatly accelerates the development. You don't have to wait for the airplane to be ready in order to do the testing. And then when you get to the airplane with your equipment, then it's not really an integration test. It's basically the verification that it works the way you expected it to work in the lab. So it's using the labs provides a big area for doing testing where you don't have to wait for the airplane to do it.
Awesome. Yeah, absolutely. And the lesson learned I thought would be worth mentioning is to give it a title, a common approach for testing. What we found when you're working with a large complex system company or team, such as an airplane, in particular an airplane, and you have all of those different engineering groups that we kind of saw in the test language map, like your flight control systems group and your landing systems group and so forth, and they typically come with an approach to how they test their system that comes from some source or another, and often that can result in many different ways of defining how a test is done and operating a test. And you need to support different test tools because different systems groups truly do have different types of tooling that they need to use to try to test their system. But having an overarching common, what we call it a test language, but a methodology that can define what that test procedure is made up of, and can be a common language, a common syntax across all groups, and then what that does is allows us to feed back up more cleanly to our requirements, our test requirements, and our system requirements, and it begins opening the door for things like getting qualification of that automated testing. Makes it easier to achieve that kind of tool qualification. It also opens the door for using formal methods for doing some analysis of those requirements and test requirements. So that a common approach is, I think, one of the lessons that we've learned, where if you truly want to squeeze the most from an automation and commonization standpoint, you really want to make sure that you achieve it. So, yeah. All right. Well, how about we move on to the Q&A? Ed?
Yeah, I think we've got a fair number of questions that have really come in, so that's really good. I'm glad to see that. Before we begin today's Q&A, I would like to ask everybody in the audience to please direct your attention to our webinar survey. It's available on the right-hand side of the presentation window. If you happen to close the survey, you can simply reopen the widget by clicking on the clipboard icon along the bottom of your screen. And I'd like to thank you in advance for filling this out, because it really does help us serve you with better with future webinars. So now let's get on to the Q&A portion of the event. As a reminder, to take part in this, just type your question into the text box that's located to the left of the presentation window, or click the Q&A icon at the bottom of your screen. If we can't get to all of the questions that are submitted today, and there have been quite a few, we'll be sure to share them with our speakers so that they can come back to you and reply to you offline about that. So let me get to some of the Q&A. Let's see. Like I said, we have a lot of them. So one question here is, congratulations on your success so far. Can you comment a little bit further on the strategic decision to integrate the new design within the current existing infrastructure? Additionally, while designed to fit within the existing infrastructure, there will undoubtedly be some need for new designs of infrastructure outside the current capabilities, like the need for bigger air stairs, scissor lifts to clear the aircraft structures, load gantries, larger capacity fuel trucks, and any other items that may be necessary to accommodate this new aircraft design. Can somebody jump on that?
Yeah, I can jump on that. I think as that's been a program requirement from the beginning, we've really been looking at all of the ground support equipment and working with our airline partners who have been wonderful to have us out on the ramp so we get real world experience. I would say to confirm and validate our requirements. So just an example, so air stairs, we're the same height, sill height and as existing, so a little bit taller than an A320. So other things like larger capacity fuel trucks, I would argue that the whole point of JetZero is we're not using as much fuel. So we can go twice as far on the same amount of gas. So in general, the plan is existing infrastructure, both from the physical aspect as well as the regulatory aspect. But undoubtedly there will be something, and I'm sure we'll work with our airline customers to accommodate.
All right, here's another one. So this person says that except for perhaps man-rated space programs or projects, this may be the most complex current endeavor out there. So can you comment on the tools, physical or electronic, that you intend to employ to manage this extremely complex mission?
Well, I suppose, from the lab's perspective for the development, we're using, like ADI has their simulation architecture and their Adept platform, which is state of the art right now. And that's what we're using in all of our labs for running the simulations. We're using standard tools that are accepted industry-wide, such as MATLAB and Simulink. And then, of course, we're using Siemens for doing requirements capture and all the process management for the program. I don't think we're doing anything that's really out of line with what the current industry is using in terms of CFD or any of the other GL Studio and some other tools like that. I don't think we're doing anything that's outlandish or extreme. We're just using those tools to probably their maximum capabilities.
Yeah, and I would add that today's webinar has been about the right-hand side of the systems engineering V, right? The testing side, the digital test enterprise. But I can comment that the JetZero's team developing on the left side of the V, including the multidisciplinary design, analysis and optimization. They're taking very, very industry-leading approach. I know that they're working with the University of Michigan, some professors who developed the open MDAO platform. So, I can't speak to details, but there's tremendous goodness that came into JetZero on the design side. And I think a lot of that came through the heritage, the team that Bethany showed photos of. It's been pretty tremendous to see how the design team has done their thing.
Right, and just to, as a secondary from this slide here, the last real slide, we're using existing tools and existing systems and components and architecture that ADI has basically for our real-time simulation. We're just employing it a little bit differently than anybody else has previously. So it's not necessarily a new tool, but we're using it a little differently to its maximum capabilities.
So another question, this is a good one. This is interesting. Is there a plan to eventually go to an autonomous aircraft without pilots, or perhaps even with just one pilot? Bethany, I think that probably falls in your wheelbox.
Absolutely. So as I mentioned, JetZero key program requirement is fitting into the existing infrastructure, and that is existing regulatory infrastructure as well. So if and when the FAA has an ability to type certify single pilot or automated pilot, or there's operations that have op specs in 121, we will continue, at least with JetZero's initial development, is fitting inside the existing regulatory infrastructure. So that is 2 pilots on the flight deck, and then obviously more as you get longer range.
So what do you guys envision as your cruise altitude for this aircraft at the moment? What's kind of the thinking on that?
So it's existing altitudes, but our plan is to certify up to flight level 450. So we can be initial cruise altitude either at 39, 41, so above the existing airline traffic, but not in unfamiliar airspace territory.
I just had some things jump around on me here, trying to catch up with it. There was another question about, so if there's a freighter version, how are you going to load it? How are you going to put cargo doors on this very sleek aircraft?
We have them on there, so we can go into more detail whenever it makes sense with the right audience, but we have cargo door configurations, and it works beautifully as a cargo airplane.
And another one here. So what sort of program development approach is JetZero and the U.S. Air Force customers synchronized on? How's that working?
Yeah, I think the question was what type, and we are doing Agile. So we are doing 2-week sprints is the program management framework that we are using in sync with our Air Force customer.
And would the, I think this is lab, I think it's supposed to be the word, provide testing capability for vibration, altitude, temperature, and humidity?
Within our test labs, we're not doing any of that environmental type testing. Most of the systems that we have are already either certified on or TSO'd into other airplanes and have been working in those other environments. So we don't really necessarily have to do that. We're using as many off-the-shelf, commonly used, or not necessarily common, but systems off of other existing airplanes as much as possible, so that we don't have to do a lot of that environmental or initial prototype development for specific components. The labs, specifically the ITF, is to evaluate and manage the data communications between the LRUs and the avionics systems, and also to manage the power requirements. And then the Ironbird, its environment is mostly to make sure there's the proper hydraulic systems integration with the flight controls and the landing gear.
Another question, is the timeline for Z4 applications rationale, considering that starting the civilian ones before military ones may have to tackle more demanding regulatory entry barriers?
Yeah, I can answer that one. I would say the JetZero strategy is to first get FAA Part 25 type certification. And we have been working with our FAA partners as well. And there's actually the military certification office inside of the FAA that we have been working with. So the intention is to first certify for the commercial passenger application. And it is, in some regards, can be more stringent. That's okay. We need to design to that to begin with. So, and then going through the military certification office to have it as a military derivative.
All right, another one. So this gentleman asks, to an aircraft designer, it appears that JetZero has found a wonderful compromise between a fully blended wing fuselage design and combining it with the traditional swept transonic wing. Can you further comment on the trade studies you have performed and how you zeroed in on the sweep and aspect ratio and designed Mach crimp point of the airfold? To an informed designer, it looks like a winner. So there's commentary there too, but that's pretty positive commentary.
If you can see the screen of our team, here I can push it there. Yeah, so I am not going to speak on the aerodynamics design, but I can tell you that if JetZero has anything, we have Aero. So it's been great about having Dr. Bob Liebeck on the team, as well as press, and we have Dr. John Vasberg. So we have just tremendous aerodynamics capability, and all of those fun details next time you're at a conference and see Dr. Vasberg. I'm sure he'd love to talk to you about those.
All right, so earlier in the presentation, you guys mentioned solving for time. So how much time and cost savings are you able to achieve?
So if there's actually some really good video out on the internet currently. Gulfstream has put out there a really good video that is just like a 3-minute blurb on using the labs. And it's a great video where Press Henny talks about it. He was the Senior VP of Programs Engineering and Test at Gulfstream. And there's Scott Martin, who's one of the test pilots there, the master test pilot. And they talk specifically about using the labs. Within the environment, Press has said that they had, I think it was over 30,000 hours of testing in the labs before the airplane ever flew. So imagine doing 30,000 hours worth of testing on the airplane after the airplane's built. Well, that's quite a bit of time. Several years of testing goes into the development of the airplane before it actually was able to fly. And so the amount of savings is tremendous. Testing things in the lab, Scott Martin references in the video how they talk about something one day, the people in the labs go in and do the testing and evaluation of it, and they have it available for the test pilots the next day. On an airplane, you can't do that because there's other things that are required, maintenance and other airplane-related specifics that you're not sure if you're going to get approval to do it the very next day. So the planning and all that is also part of the equation. In the lab, you can go and do things a lot more quickly, a lot more versatility within the lab to do things that you wouldn't do on an airplane because it could put the airplane and the flight crew at risk. So having the labs available to do those extraneous things, to fail 40% of your flight control surfaces and try and fly it, you wouldn't want to do that on the airplane, but you can do that in the lab. So the labs provide a lot of versatility and a lot of options for testing that the time savings is one thing. Some of the other capabilities, you can't quantify it very easily as in a monetary sense as to how much it actually saves, but I can tell you it's a whole lot.
Yeah, and I've heard, it's always the tough question, right? Because there's just nobody has access to all of the data required to really assess the true time and cost savings. But I've had discussions with executives who firmly believe that they're cutting their program duration in half, and the associated costs come along. I mean, of course, you're investing in what is not low cost facilities and assets. But if you talk about cutting a commercial aircraft program in half duration, that's just tremendous return on investment.
Well, and in addition,
one last question. We are almost out of time. So,
okay. Here, Ed, let me finish.
What kind of hardware are you using to build up the labs?
So within the labs, we're using, of course, ADI's real-time operating system. It's a Unix-based operating system on the platform for simulation. And then we're using, MATLAB and Simulink is the basis, the language that we're using for developing all of our simulation models and doing a lot of the interaction. And then we have just regular PCs and such for doing some other inputs to support all of our equipment. And then we use wherever possible, airplane hardware and airplane systems for displays, inputs, controls, buttons, switches, and whatever else.
And the lab's computing equipment and so forth is it's off the shelf computing equipment. It's the kind of stuff you can buy off DigiKey or you can buy online, and that gives a lot of benefit for long-term maintenance and support of these labs.
So before we sign off, I want to thank our presenters, Bethany, Scott, Stephen. This was fascinating. Wow. I'm blown away. I also want to thank your sponsor, Applied Dynamics. So everybody that was taking part, within the next 24 hours, you're going to receive a personalized follow-up email. It has details with a link to today's presentation on demand. So if you have any of your colleagues who were not able to join us today and take part in this, hook them up with that on-demand version, and you know, they'll get it. So there you go. I'd like to thank everybody for attending today, and all of you have a great, wonderful remainder of your day.